All right. In his best-selling 2014 book, Yuval Noah Harari discusses a brief history of humankind. And one of the core ideas from this book is the importance of stories. The words and stories we use as humans is the master key to our success as a species. Our ability to get ourselves together behind an idea, whether that be a religion, the nationality you are, or the country, the company you work for, and the values that company has. Our ability to get ourselves behind an idea at scale is what differentiates us from other species. Now, some of you might be really confused at this point, thinking that you're at NDC London. Why are we learning about a history of humankind? And that's okay. If you're furiously checking your agenda, you are in the right place. This is going to be a talk about event-driven architecture. The reason I start there is because event-driven architecture is fundamentally a communication pattern, a way of modeling the integration between two systems. And that's what you're here to learn about today. We're going to talk about some of the practical implementations of event-driven architecture. We're going to start from some of the beginner concepts and work through some more intermediate patterns. I'm James Eastham. I'm a senior cloud architect at AWS. And for all of you non-AWS people in the room, don't worry. This is not going to be death by AWS service icon. In fact, this is just a really simple talk, really simply about boxes and lines. And I want to start today by being really, really honest with you all. I've built event-driven systems in the past, and I've got them terribly, terribly wrong lots and lots of times. And that might make you think this is a really odd way of starting a talk, admitting that I've really badly built event-driven systems. How many people here have built something that's failed at some point? You can be honest, this is a safe space. Yeah, everybody? Okay, good. And how much did you learn from that failure? One of my old mentors always said to me, you learn so much more in failure than you do in success. We literally used to walk into pre-sales meetings with customers and say, we will do this well because we've gotten this wrong so many more times than you have. So that's what we're going to talk about today. I'm going to try and show you some of these challenges, some of these things you might hit as you start to adopt event-driven architecture. And for the rest of this talk, I want you all to put on your imagination hats, because there's something I love talking about almost as much as event-driven architecture and serverless, and that is pizza. Who else loves pizza? For anybody who's still got their hand down, really? For the rest of this talk, you are now all developers for a completely fictional pizza company called Plant-Based Pizza. You've already adopted microservices. These microservices are communicating right now over HTTP, request-response style communication. This works well, it's functional, but it's giving you an awful lot of challenges. That's because you've got this order processing service that's the core domain. This is fundamental to your application. If people can't place their pizza orders, then really what is the point of a pizza delivery company? And this order processing service has a dependency on all these other services, on the pickup service, the delivery service, the kitchen. And you also need to add a new loyalty point service to allow people to build up loyalty points. It would be amazing if pizza places did this, because I'd have so much free pizza by now. Then this really is a problem of coupling that you've got here. All these services are really tightly coupled together over HTTP. And I'm sure you've all heard the adage in software before that you should aim for high cohesion and low coupling. And cohesion, you've kind of already solved a little bit. Cohesion is the idea that things that change together should live together. And you've got microservices. You've broken your system down into these small, independently deployable pieces, so you've kind of solved that. Coupling, however, is a slightly more nuanced problem. And that's because there's lots of different types of coupling. You've got location and runtime coupling. That's primarily what you're dealing with request-response style communication. At the time you need to make a request, you need to understand the location of a specific service, whether that's the IP address, the domain name. But you've also got other types of coupling. You've got semantic coupling, data format coupling. Are you using binary data, protobuf, JSON? How do you handle null values, ints, strings? What casing are you using in your JSON? Is it camel case? Are you using hyphens? Is it some weird combination of underscores that only makes sense to you and your business? These are all different types of coupling that you need to work with. And of course, you need some coupling. Without coupling, it will be really hard to make these microservices actually do anything. And there's an appropriate level of coupling to aim for. And I really love this quote from Gregor Hoppe. An appropriate level of coupling depends on the amount of control you have over the endpoints. And what I think Gregor means by that is that if you are working on a team that maybe manages 2 or 3 different microservices, coupling them services together more tightly isn't necessarily a bad thing. Because you control the release cycle, you control the SLA, you control the schema of these systems. But once you start integrating with a system outside of your control, you want to try and reduce this coupling as much as possible. Whether that be a third-party SaaS product that exposes an API or another system inside your organization. So if it's coupling that's the problem, and there's an appropriate level of coupling to aim for, why does it help to be event-driven? Starting with why is always a really important thing to do in software. Layla talked about that in her keynote yesterday. So let's come back to this use case that you need to implement now. You need to add this loyalty point service to your system. So you build the loyalty point service, microservices, you deploy it independently, excellent. But now you need to go and make a change to your order processing service to actually tell the order processing service to make the call to the loyalty point service to add the loyalty points. And when you think about that, is that really logically the right thing to do? Should the order processing service care about the fact that people are collecting loyalty points? Probably, possibly not. And you can make that same argument for other parts of the system as well. The kitchen service, the pickup service. Should the order processing service actually care that all these things need to happen? In some cases, yes, absolutely. But in not all cases. There's another problem here. If you run this communication over HTTP request response, you've got that runtime coupling. The loyalty point service needs to exist at the time the order processing service is doing its work. What happens if this happens? The loyalty point service goes offline. Now you've got a service that's not in the core domain, it's not the core part of the order processing flow, but it has the potential to take your order processing service offline. Now, I realize I'm massively oversimplifying that. It is possible to build microservices in this way that are resilient. You can use things like circuit breakers and backoff, so that is possible. But event-driven architecture can help you minimize that. So before we get into some of the technical patterns, let's just take a step back for a second. Just talked about the importance of language and words. So let's ensure we have this same shared definition of what all these things mean. What does it actually mean to be event-driven? Sounds a little bit buzzwordy, right? Event-driven. We're all talking about event-driven architecture nowadays. The most succinct way I found of putting this is something I've taken from one of Martin Fowler's talks on the topic. And at its core, event-driven architecture is about reversing dependencies, reversing the lines of integration. So now instead of the order processing service needing to know where all these services are, all these downstream services are now reacting to events that the order processing service is publishing. So that's what it means to be event-driven. It's about reversing dependencies. Let's take a step back even further. What actually is an event? What is an event? In my opinion, an event is an immutable fact. It's something that's happened in the past. It cannot be changed. The example I like to use here is that of a light switch. It's February, we're in London, it's dark, it's horrible. You get back to your hotel room at night and it's pitch black, and you need to get some light in the room so you can see what you're doing. So you hit the light switch. And that raises a light switched on event. You can't unswitched on a light. What you need to do to take the light out of the room is to hit the light switch again, and that will give you a light switched off event. The light will leave the room. Light switched on, light switched off. They're irrefutable. They can't be changed. They have happened. So if that's the definition of an event, what does it mean to be event-driven? And I think there's sometimes some confusion here between event-driven systems and an event-based systems. And that might sound like semantics, but I think there's a key distinction. And the event-driven system is where your system functionality is driven by business events. And that's important. Because we've been building event-based systems for years and years. I started in software building with Windows forms. Who remembers Windows forms? Who's still managing Windows forms? Who's still building a Windows form? Some people, amazing, wow. In Windows forms, you triggered functionality using things like button clicked, mouse hovered, window resized, and then something happened after that, some functionality executed. And even building systems in more modern ways, you can do the same thing. If you drop a file into an Amazon S3 bucket, there's that first AWS service name, that will raise an S3 object created event. And you can trigger functionality off these events. But that doesn't make it event-driven. An event-driven system uses events like these. Order confirmed, pizza boxed, staff member clocked in. These are events that are unique to your business. You could look at two identical businesses in the exact same domain, And whilst they might both be triggering functionality off things like S3 object created, they will have a fundamentally different set of business events that are unique to your business. You're letting the language, the story of your business, drive its technical implementation, and that's what event-driven architecture can give you, this shared language. The other thing you might hear when you learn about event-driven architecture is that events are first-class citizens. That sounds like another buzzword, right? What does that actually mean for an event to be a first-class citizen in a system? How many of you have heard of the idea of API-first design? Yeah, some people have, some people haven't. API-first design is this idea of when you start building a system, the first thing you do is design the API. You design the point of interaction, the integration. So when you want to glue systems together, you have this agreed contract. So with event-driven systems, events being first-class citizens means that you default to event-first design. The first thing you want to do is actually design your events because they are the point of integration. They are the point of coupling that you have in your system. And it's not as simple as just adopting events. There are lots of different types of events you'll likely see in your systems. The first of those is a notification event, or what can be known as a sparse event. This is a really small, really simple packet of data that simply notifies other systems that something has happened. They're typically quite lightweight. And this is where you start building out this event-driven system for plant-based pizza. You introduce events for the integration between the order processing service and the kitchen service, and you publish an order confirmed event. So somebody places an order, they're waiting for the pizza, the kitchen receives this order confirmed event, it has an order ID, and the kitchen goes, fantastic, what do I actually need to cook? What's actually on this order? So then the kitchen service calls back to the order processing service, says, excuse me, Mr. Order Processing Service, what's actually on this order? What do I actually need to cook? And the order processing service responds, and everyone's happy, right? And this is a system I've actually built before. I've done this exact same integration before in the past. And it works really well functionally because you receive the event, it's nice and small, it's lightweight, and you call back and get some more information. And then you add another set downstream service. And then you add some more downstream services, and some more downstream services, and some more downstream services. And eventually, all of a sudden, this happens. Everything falls over because now you've got this potentially infinite number of downstream services that are all making calls back to get more information about that specific order. Yet a core principle of event-driven architecture is that services producing these events should be completely unaware of their downstream consumers. But yet, if every single one of these downstream consumers needs to call back, they are kind of aware, right? So is there an alternate approach you can take here? And there is, and this comes back to this idea of different types of events. Another type of event you will see is event carried state transfer, or a more fat event, as it can be commonly known. So this is an example of a sparse event, or a notification event. You've just got an order ID, so order confirmed, just an order ID. With event carried state transfer, or fatter events, that event will look a little something like this. So you see you've got a lot more information here now. You've got more information that the downstream consumers can use to actually perform some functionality without needing that callback. So the kitchen can consume this event. It's got the list of items on the order, so now it knows what it needs to cook. Perfect, happy days, right? So which one of these is the right one to choose? Do you use fat events? Do you use sparse events? Hold that thought, we'll come back to that in just a second. Let's stay with the theoretical just for a minute. At its core, an event-driven architecture is made up of three parts. You have a producer, a consumer, and some kind of event broker in the middle. That might be an event bus. Equally, you might see a queue or a stream or a topic. There's just some kind of broker in the middle that's in charge of routing these events from one place to another. And the first thing you'll notice is that the producer and the consumer here have no idea each other exists. The communication is managed by the broker. The core integration pattern at work here is the publish-subscribe pattern. You have a publisher producing events, and you've got n number of downstream consumers that are all consuming these events. And as a producer in an event-driven system, as a publisher of these events, your real responsibility is to make sure you stick to that design you agreed with. Because the schema of your event, the format of that event, is the biggest part of coupling that you will see in an event-driven architecture. So although you've removed that runtime coupling, because now producers and consumers don't know each other exist, you still have semantic coupling. The format of that event is really, really important. So as a producer, it's your responsibility to try and minimize breaking changes and to stick to that contract that you agreed on. There's some things you're not responsible for anymore, though, and this is where it gets really interesting. You're not responsible for how your events are used. Your responsibility is simply to publish the event. And what downstream people choose to do with that is not your problem. And the other thing that's not your responsibility, when you compare it with HTTP, is the constraints of your downstream consumers. So if you think about when you're making a HTTP request, you need to understand what kind of throughput that downstream system can support. What rate limits does it have? You need to understand the format of the API that API has. That's now your responsibility, but then you're responsible for the constraints of a system outside of your control. And with event-driven architecture, that constraint, that understanding of constraints switches to the subscriber's responsibility. And this makes more logical sense if you think about it. I should own the constraints of my own system. So as a subscriber to events, you need to control your own ingestion rate. You need to control the load on your system. And another place where you can get into trouble here is hooking your systems directly up to the event bus. Because remember now, producers don't care about how their events are being used. They're just going to publish events as and when they come in as fast as they can. And if you're not careful as a subscriber to an event, you can really easily overload your own system. So what I always recommend when talking about event-driven architecture as a subscriber is protect yourself against this kind of flaw. As opposed to hooking a piece of compute, your application, directly up to the event bus, which then couples you to a system completely out of your control, instead introduce some kind of queue, some kind of durable storage that you understand. So when the event hits the event bus, it comes down to your microservice and it hits some kind of queue. It's stored there durably. And then you can do some work off the back of that queue. And if you get some increased load, everything just builds up in the queue and you can simply process that at a time that suits you. Another more subtle benefit of event-driven architecture, and I promise we'll get out the theoretical in just a moment, another subtle benefit of event-driven architecture is around communication. Obviously, this is a technical pattern, technical communication between systems, but it also really helps at a human level. How many of you sat in a room with a non-technical person and just seen their eyes like glaze over a little bit as you start talking about microservices or REST APIs? Yeah, they kind of just go like this a little bit, like, what are they talking about? When you start using event-driven architecture, it eases this communication because you can walk into a room now and say, what should happen after an order is cancelled? How should we deal with an order completed event? You can have these kinds of conversations. It makes this communication easier. And that's because, to come back to this quote from earlier, EDA is fundamentally a communication pattern, a way of modelling the integration between your systems. So let's actually get a bit more practical now. Let's start to model this integration in plant-based pizza. And to do that, let's start with how things are working today. So right now, a request comes into your order processing service. That makes a call to the kitchen, say, hey, can you please go and cook this order, please? The kitchen responds after that order has been created and says, yep, this order is now finished, at which point the order processing service will make a HTTP request to the delivery service responds, call to the brand new loyalty point service responds. And you look at this right now, and even in this simple example, there's quite a lot of coupling here. There's quite a lot of runtime dependency. And this is what we're going to work to remove as you start to adopt event-driven architecture. And the first question that might be in all of your minds now is, how do I actually understand the events in my system? If every single business has its own unique set of events, how do I understand what them events are? And I want to come back to the same image from earlier, because there's something in this image that's really quite useful when it comes to event-driven architecture. And that's the idea of event storming. Who's heard of event storming? Who has done event storming? It's actually been through and done an event storming workshop. Okay, some of you have, some of you haven't. Really coincidentally, there's actually a thing on the wall over there, which is actually a really good example of event storming. That wasn't planted there, that just happens to be there. Event storming is an idea that was populated by Alberto Brandolini. And quoting directly from the website, it's a fantastic way to increase collaboration across siloed boundaries. Sounds fantastic, right? And one of the things you can do with event storming, again, quoting from the website, is that it can be used to design clean and maintainable event-driven software to support rapidly evolving businesses. And I'm sure many of you are dealing with change in your systems, things that change over time. So this isn't going to be a deep dive into event storming. That's a whole talk in itself. But let's just quickly touch on what event storming is. So you run event storming workshop style. You get every single possible stakeholder into a room together. Business people, technical people, everyone's there together. Everyone has a pack of Post-it notes, and they're all sticking Post-it notes on the wall. They're sticking Post-it notes to understand what the events are in a system. Things like order created, payment processed, order delivered. They're sticking Post-its on for the commands, the things that trigger these events to happen, and Post-it notes for the queries. And this, importantly, is a conversation focused on the business. If you catch two developers, and there always will be two developers sat in a corner talking about how they could build this on Kubernetes and how complex that would be, and tell me it will be complex if it's Kubernetes. Bring them back into the room, bring them back to the business conversation, because that's what it's all about. The core thing that you get out of an event storming session is a shared language that you're going to use across the entire business, both in the technical and the non-technical. That's the core thing. So the other thing you commonly hear when you hear about event-driven architecture is this idea of evolvability. If you've got this stream of events that are just flying around everywhere, you've got this central event bus and producers and consumers don't know about each other, doesn't that make your system incredibly evolvable? Because you could just add a new service, hook into that event stream, and now you've got this new service and it's event-driven and everything's magical. Not always that simple, of course. Nothing's ever that simple. So let's come back to this fat event, this event carried state transfer. You're publishing this order confirmed event. And actually, because your pizza restaurant is so popular, you've now gone global. You've gone multinational. So now you need to start adding the currency to this order confirmed event. So what you do is you take that order value property and you change that to be an object. So instead of just publishing the value as a decimal, you're now publishing an object that has the value and the currency of that value. Who can see a potential problem with this? Yeah, everybody. Because what you've done now is you've broken the contract of your event. You've changed the schema of event. And you might think, well, when we did that event storming session, it's only the kitchen that's really interested in this event, and they don't care about the value. They only care about the items on the order. And then you realize that a downstream service had been added to support analytics, to support reporting, and you didn't know about it. Remember, producers are unaware of their consumers. And now you've just broken a system completely that you didn't know about. You've just taken it offline. So what do you do now? How do you handle this? And I'm going to put a really dirty word on the screen now, and I'm sorry, you're all going to get shivers down your spine, and I really, really apologize for it. It won't be there for long, I promise, and that word is governance. Everyone's favorite word as a developer. There's tingles of bureaucracy. You love it. And governance is really important with event-driven architecture because you've got these systems that just don't care about each other. You need a way to govern these events, and this doesn't have to be bureaucratic. This can use a process that you're all probably familiar with as developers. And that's the idea of an RFC, a request for comment. So when you're thinking about changing an event, instead of just changing the event without telling anybody, make it collaborative. Raise some kind of RFC. Let people comment on the change that you're thinking of making to your event. Relatively simple, but it's a really powerful way, and it's not really that bureaucratic. Hopefully you've all recovered from that word being on screen now. The other thing you can do at a more technical level is to think about the schema of the event that you publish. Rather than just publishing an event that is just the order confirmed event, introduce this metadata data pattern. Again, the schema of your event is the tightest form of coupling in event-driven architecture. So at a top level, splitting your event down into a metadata section and a data section helps you to stay evolvable. So the data property here is the actual event payload. This is the bit of the event that's unique to the event you're publishing. For every single type of event in your system, this data property will be completely different. It's the metadata property where things get really interesting, because this metadata property is going to have the exact same schema across every single event in your entire organization. They're all going to have this metadata property. And they're all going to have the same properties inside this metadata property. One of those will be the event type. What type of event is this that's being published? In this case, it's an order created event. An event ID. The event ID is a uniquely generated identifier generated at the point of publish. And this allows any downstream consumers to more easily implement things like idempotency. You can look at this event and be like, have I seen this event before? Yes, I have. I can just ignore it. The event date and the event time, this can help you to understand ordering of events if that's something that's important to you. And finally, with this conversation around evolvability is the version number. You see you've got version and V1 here. Including a version number as part of your event more easily allows you to introduce breaking changes. So let's come back to that same example where we need to change the value from a decimal to be an object that has the value and the currency. So right now, the order processing service is publishing version 1 of that order confirmed event, and the kitchen service is consuming that. All your downstream consumers are consuming order confirmed version 1. And then what you can do is also start publishing version 2 of your event. And nobody might be interested in this event right now. You're just publishing it, and it's going to be really sad because nobody cares about it, but it's going to be there, ready. And then you can put out a notification to the rest of your company saying, hey, we've now got version 2 of this event. Can you please all switch over to version 2? We're going to depreciate version 1 on day X. And over time, all of your consumers can switch over, start consuming version 2, and eventually, over time, you can stop publishing version 1 of the event. So as much as possible, of course, try and avoid breaking changes. But if you think you're never going to make a breaking change, I can tell you now, you're going to be wrong. You will eventually, over time, need to make a breaking change to an event. So that leads us back to this question. Fat versus sparse events. What's the right one to choose? And unfortunately, I'm not going to give you a definite answer on this because, as always, it depends. Feels like a cop-out, I know, but it genuinely does. So fat events obviously reduce that need for a callback. They reduce the need for systems because all the information a downstream system could possibly need is in that event that gets sent. The downside of that is that you get more coupling at the schema level. It becomes more challenging to make changes to that event over time because you don't know which bits of that event different systems are interested in. So based on that argument, that might lead you to say, well, long live the sparse event. Let's just publish sparse events everywhere. But as was described, when you do this, it can become challenging. If you take this to the absolute extreme and you only ever publish sparse events, and to stop this risk of callback, you just don't allow systems to make a callback. This would work, it will give you sparse events, it will reduce that coupling, but actually this isn't really that practical in the real world because then how would the delivery service here know what it needs to deliver? It just wouldn't. So the other option you have here is to use more sparse events, but instead of just publishing a single identifier, include multiple different identifiers. And when you think about the logical flow of this here as you order a pizza, you're on your app, you're hungry, you're ordering your pizza, and the first thing you'll likely do is add a delivery address. And that delivery address is going to go to the delivery microservice. Remember, microservices own their own data, they have one responsibility. So here, the delivery service should own all the delivery addresses, and the order service should own all the orders. So you add your delivery address, and that will go into the delivery service, and that will get stored with some kind of unique identifier. And then after that, you'll do the submit order, you'll create your order. And when that create order request goes in, that will include the identifier of the delivery address that needs to be used, so that when that order confirmed event gets published, you can include the order ID, but you can also include the delivery ID. So when the delivery service consumes this information, it can be like, I know what that delivery ID is. Go and get that, and it can set the right delivery address. So you can still keep sparse events, but you don't need to really, really minimize that down. You can include other identifiers as well. The other option you've got here is a pattern called the enricher pattern. And the enricher pattern allows you to enrich event information as it moves through the system. So as a producer, you might still publish a sparse event, and the vast majority of downstream consumers might actually only be interested in that sparse event, and they're happy with that. Some services might need that additional information. So you might, at the point of publish, maybe put that information in a shared location. That might be another API that's exposed specifically for these callbacks to protect your main system. It could equally be a shared service like Amazon S3. There's the second AWS service name. S3 is really good because it's scalable, it's durable, it's available, and it's really easy to share information across different accounts, different systems. So you could potentially drop some data into Amazon S3, put a pointer in your event payload, so when a consumer consumes that event, they can actually reach out and grab that additional information if they need it, but you're protecting your main order processing microservice. Whichever type of event you choose, fat or sparse, and you likely have a combination of both, at least if you're doing this at scale, embrace that metadata data pattern, include a way to have this additional metadata as part of your event. So the other word you'll likely hear a lot as you talk about event-driven architecture, and I've said it a few times already, is the word asynchronous. What does it mean to be asynchronous? Now, if you're a developer today who's used to making a method call or a HTTP request, this can be a little bit of a paradigm shift. I know when I first started building event-driven systems, this took me a little while to get used to. Because now you're in a place where instead of everything happening in process, you're now publishing an event. So you might publish your already confirmed event. And at some point, hopefully, potentially, maybe later, an order cooked event will come back from your kitchen service. But you've actually got no way to ever guarantee that the order confirmed event ever makes it to the kitchen service. It's not something that's your responsibility. You don't need to care, but obviously the business cares. The person who's ordered the pizza cares about that. And this is the problem here with consistency. And with consistency, you've got two types of consistency. You've got strong consistency and eventual consistency. And I want to try and explain the difference between the both using the pizza restaurant. So you only put them imagination hats on again. Imagine you've placed your order and you're going down to the pizza restaurant to pick it up. You're going to collect this order. You walk into the pizza restaurant, the smell hits you in the face, pizza's amazing. You can almost taste it, you can see the pizzas being made. Sometimes I give this example just before lunch and people literally zone out at this point. They're like, pizza. So you're there, you're waiting to pick your pizza up, you're hungry, and what you need to do first, you need to pay for that order, right? And you've got two options when you come to paying for your order. One slightly more common than the other nowadays. The first option you have is to pay with cash. You can take out your purse or your wallet. You can take the cash out, hand it over to the cashier. They'll take that money, put it in the till, you get your pizzas and you go on your way. And that's an example of a strongly consistent transaction because at that point you can absolutely guarantee that that money has changed hands because the money's sat in the till. And if that was to fail for whatever reason, let's say you're here in London and you try and pay with, I don't know, dollars, you're likely going to get that money back and you'll have to retry, you'll have to go again. This is what you're used to if you're doing request-response style communication. The other option you have when you pay is to pay with your card. And when you make a card transaction, all you're doing is making a theoretical guarantee that at some point in the future, that money is going to move from your bank account to their bank account. I'm sure you've all been there where you've paid for something, you've paid for your pizza, you've got your phone out onto your bank statement and the money's not actually shown up yet. And you walk out thinking, yes, free pizza, look at that, amazing. And eventually, sometime later, that money will eventually move over to the pizza restaurant's account. Now that is an eventually consistent thing that's happening. Eventually that money's going to change hand, but it isn't. And I don't know if you caught Sam Newman's talk yesterday, but I actually like a phrase he used, which was eventual convergence instead of eventual consistency. Eventually, over time, these systems will converge on the same view of the world, providing people stop publishing events. And one thing you'll need to do with event-driven architecture is just to embrace eventual consistency. This is one of the trade-offs you have to make when you're building event-driven systems, is that you need to embrace this eventually consistent way of looking at the world. So now everything's fantastic. You've implemented an event-driven architecture at the pizza restaurant. Events are flying around, everything's loosely coupled, things are wonderful, until of course something changes, because it always changes. And what actually happens now is your business leaders come along and they say, you know that loyalty point service that you spent so much time building, you put all that blood, sweat and tears into, we want to get rid of that now. We're going to replace it with a SaaS product. Get rid of that. We don't need that. We don't want to build this custom. We want to use something that somebody else has built. And this causes your event-driven way of building a problem because this third-party SaaS product isn't event-driven. It exposes a HTTP API, and that's what you kind of wanted to get away from, right? So how do you handle this kind of HTTP communication in an event-driven world? Because you're likely going to see that somewhere, whether that be a third-party API or another system inside your organization. And the way I like to think about this is that you would still have an event-driven microservice managing this communication. You would still have a loyalty point service. And the team building that loyalty point service is in charge of managing that integration, right? What that might look like is something like this. So you've still got your event bus, you've still got your order completed event hitting the event bus, and then you've got a service that's only job is to take that event and translate that into something that the loyalty point service can understand, that third-party API, make the call to the third-party API, the response comes back, and then you might publish another event, a loyalty points added event. Now you'll notice here that I've put a queue in the middle here, and this is important. If you think back to Gregor's quote from the start, the appropriate amount of coupling depends on the level of control you have, and you now have no control over this third-party API. You don't control the uptime, you don't control the SLAs, the throughput, the rate limits. So introducing this queue ensures you can keep this amount of durability. The event, the order completed event, can hit the event bus, come through into a queue, and you can work off that queue and process to the third-party API as and when you need to. Another really useful place for this pattern is as you have teams in your organization who are starting to adopt event-driven architecture. They're kind of interested, they want to start doing it, but they're not quite ready to get rid of their ASP.NET web APIs running on containers. They just love them so much. So what you can do is you can still have that web application that exposes a HTTP endpoint, but you can allow teams to take these small baby steps into the event-driven world to start building a pattern like this. They can get used to reacting to events, but yet the core bit of their system is still HTTP based, and they can just pass that event on. It's a really nice step into the system. So this gives us now a way to integrate with things that aren't necessarily event-driven. We can integrate with these HTTP-based systems. What happens in an event-driven architecture when things go wrong? Who's ever had a system break for a reason that they didn't even know was possible? Yeah, hopefully every single hand. If they haven't, I want to speak to you afterwards because I want to know how you found out. What crystal ball do you have? And this is where observability is really important. And obviously observability is really important in every single type of system that you build. You need to understand what's going on inside your system. But with an event-driven system, it gets really tricky to understand cause and effect. Because when you've got request-response style communication, service A calls service B and service B responds, you can kind of see that that's happening. But in an event-driven system, you're just publishing an event, and at some point, someone might maybe be interested in consuming that event. So you want to keep your system observable. You want to be able to understand this cause and effect. And a really simple way to ensure you can do that is just to revisit that metadata data pattern from earlier. And we'll just make a small change to it. We're going to add two additional properties, a trace parent and a parent span. This assumes the use of OpenTelemetry here. And if you aren't using OpenTelemetry, then this could equally just be a correlation ID, some common identifier that always gets passed as part of the event payload. And what this allows you to do is it allows you to continue this trace, it allows you to link these traces together, it allows you to understand cause and effect more easily. Of course, in your consumers, you still need to handle all this fact. You need to handle the fact that maybe that trace doesn't exist anymore, potentially. But at least it allows you to give the possibility to determine cause and effect. So again, just this is another example of being really intentional with how you design the schemas of your events. If there's one takeaway from this talk, that is it. Be intentional about the way you design your events. So let's talk about boundaries now. What happens at the edges of a system? Because surely at some point in any event-driven system, you're going to need a request response somewhere, right? That might be a mobile client, that might be a web browser. So how can you actually manage that? How can you manage these calls from external systems that might not be event-driven in an event-driven way? And I'm a really big fan of having these really thin actual synchronous API layers at the boundaries of a system. So you might have a really thin order API that takes that request in, the create order request, does a little bit of validation, stores that request in a database of some kind, and then goes on and publishes the event to the event bus. And then you have your downstream consumers who are then reacting to that event, and all of the functionality is happening asynchronously. Your events are driving your business functionality, remember. Now, what happens here for your get order request, though? Because if all this stuff is happening asynchronously in the background, and then somebody wants to check the status of the order, I'm sat at home really impatiently refreshing the screen to try and work out where my pizza is, how do I understand the latest state of the world? Because everything's happening asynchronously, remember. And this is where we need to make a distinction between commands, events, and queries, the three different things you are likely to see in any system. And commands and events are kind of similar, really. They're both going to cause something to happen. The difference is really mostly just a statement of intent. With a command, I'm telling you, can you do this thing for me, please? Whereas with an event, I'm just reacting to something that has happened. And then a query is me asking for a specific piece of data, a specific view of the world. Can you tell me the status of this order, please? Order processing API. So to revisit the same example again, the command comes in to create the order. That's the web client or the mobile client saying, can you create this order for me, please? The event gets published to the event bus, the downstream functionality starts happening, and then eventually your downstream systems will publish an event when they're finished with their work. So the kitchen will publish an order prepared event. And all you need to do to make sure you can update your view of the world is just to add some kind of service inside your order processing service that's interested in these events that downstream systems are publishing. So you hook into that order prepared event, and although you're not going to trigger any functionality off the back of that, you're still interested in it, because then you can just update the status of the order in your database. And this allows you to keep this common view of the world as events are happening in the background asynchronously. I want to quickly discuss the idea of asynchronous commands. So although event-driven systems, typically everything is an event, and this might offend some of the event-driven purists in the world, but sometimes you might also want to process a command asynchronously. So let's imagine the scenario where your order processing service needs to send an email. So send an email saying, hey, here's your order details, or the receipt of your order, whatever that might be. And you could build that in a HTTP-based request-response style communication. So the order processing service makes a call to the email notification service, can you send this email, please? And a response comes back. But actually, is this really what you want to do? Should the order processing service be blocked whilst an email is being sent? Probably not. So you probably want this to be non-blocking communication. But actually, you still want to say, I want to send an email. You could equally implement this in a completely event-driven way. So the order processing service publishes an order confirmed event. The email notification service is interested in that event, and it uses that to then go and send an email. But actually, is this responsibility right? Because now the email service needs to understand what should go into that email. What's the subject? What's the body? And is that right? Is that responsibility right? Should it not be the order processing service's responsibility to determine what actually goes in that email, and the email service is just there to send emails out, however it does that? So you kind of want this to be a command. You want this to be, I want you to send an email, but you might not necessarily want it to be completely request response. You might not want it to be blocking. So you can do this in a similar way. Your email service can still expose an endpoint of some kind, but as opposed to that being a HTTP-based endpoint, that could just be a message channel. This might be a topic, this might be a queue, doesn't really matter, but it's asynchronous. So the order processing service can still send a send email command. I want you to send an email for me, please. And in the payload of that event, it will include the to, the from, the subject, the body, that kind of common things you will see in an email. You'll notice, interestingly, in the metadata property, if you can see that, I've also got a response channel. I've got one more additional property in that metadata section. And that response channel is what allows you to build this request-response communication in an asynchronous way. Because now your email service can process that request, send the email, and after it's sent the email, it knows where to send a response back to, and it can send a response back to that response channel within the order processing service. Now, in the case of an email, you might not necessarily want to do that. You might not care about a response, but this is a way you can start to do request response in a way that isn't necessarily blocking. Now, of course, in some cases, you probably will want blocking communication. If you're taking a payment, for example, you're going to want to know that that payment has happened before you send somebody a pizza. But in a lot of cases, it might not necessarily need to be synchronous. So we've introduced commands, events, queries. We've introduced some of these different ideas, and there's one more pattern I want to introduce you to now that plays really nicely with event-driven architecture. And to be absolutely clear before I put it on screen, this is not a prerequisite of building event-driven architectures. You do not need to be using this pattern to build with EDA. And that pattern is command query responsibility segregation, or CQRS. Who is familiar with CQRS? Who's used CQRS? Hands everywhere. Awesome, I can fly through this and we can all go and get a coffee then. So in CQRS, you split your system into two completely independent services. One for processing commands, one for handling queries. So the create order request will come in to your order API. That will do a little bit of validation, maybe store that in an orders database and publish an event to an event bus. All your downstream consumers are interested in that event, and your query system will also be interested in these events that are happening, and it will use that to update its view of the world. So here is this specific view that people can then query. So let's start to bring all of this together now, bring together this entire order processing flow. So the create order request comes into the order processing command service. I've not yet thought of a better name for that, but that's what it's going to be for now. And that service will publish an order confirmed event. That order confirmed event, your kitchen service is interested in that because it's, needs to know what, when that happens, it needs to know it needs to place the order, create the order. But actually your query system is also interested in that order confirmed event, and it uses that to update the status of the order in the query database. Once the order's been created, the order prepared event gets published. The delivery service is now interested in that order prepared event because it can now go and deliver the order. And again, your query service is also interested in that order prepared event because it then updates its view of the world, and it can tell me, furiously refreshing my phone, that this order is now out for delivery. Then the get request comes in to actually get the status of the order. That's me refreshing my phone, and I get the view of where that order is up to. And I want to zoom in on this bit of this interaction just for a second. So the command comes in, it gets validated, and the order data gets stored in the database, and then the event gets published after that. What happens if that event fails to publish? What do you do? Because now you've got this order in the database, but the event fails to publish, which means the kitchen's never going to start creating it. And you could at this point return an error code to the caller and get the person to try submitting the order again, but is that really the right experience for your user? Is that really the best thing to do? And you might have seen an example of this if you've ever tried to pay for an order on Amazon with a card that's expired. So you place the order, and on the website you get the order number, you get an order confirmed page, and then a few minutes later you'll get an email that says payment failed. Please go and update your payment details. That is an example of this happening. The request is always received into the system, and then at some point later, after this downstream functionality has happened, a caller comes back. So this is something that you need to work with. You need to handle this fact that a request can come in, but the event might not necessarily be published. And there's a couple of ways you can handle that. The first is using the outbox pattern, a transactional outbox pattern. So with an outbox pattern, at the point you write the data to the main database, you write the order data, you also write the data to a secondary table, it could be called Outbox, something like that. And you wrap that whole thing in a transaction so that if one fails, the other one won't happen either. Then you can have a separate piece of functionality working off the back of that Outbox table that's picking up all the data that hasn't yet been published, all the events that haven't yet been published, and then distributing them out to the event bus. This works really well, but it does mean that you need to manage two separate tables. You've now got your main table and you've got an Outbox table. And you'll need to manage that Outbox table because it will just grow and grow and grow and grow. You need to be clearing it down. So an alternate option that I found works really well is to use change data capture, providing you use a database that supports change data capture. And what change data capture allows you to do is to react to the stream of changes that are coming out of your database. So as a record is written to the database, you can stream that, you can react to that, and you can publish events off the back of that. If you're using a service like Amazon DynamoDB, third AWS service name, then you could turn on DynamoDB streams and just react to that stream of changes in your database, and you can use that to publish events. So to kind of stitch this all together now with CQRS, so you've got the request coming in, the command coming into your order processing service. That's a random arrow. You've then got that being stored in your main order database. You're using a transactional outbox pattern or change data capture to stream that out to some kind of publisher that's then publishing the event to the event bus. Your query service is hooked up to that event bus, creating its own view of the world, a specific view for a specific use case. So when the GET request comes in, it can do something specific with that. And where this gets really powerful is that it's the command database, the database on the left there, that's the source of truth for your system. That's the real database. The query service is just a view, a projection. And this allows you to get some really nice optimizations because you can then optimize the format of that data structure in a way that suits that specific GET request. So you'll see here that that table on the right only has the status, the value, and the item count because that's what the view in the UI needs. It only needs that information, so let's store it in that way. And equally, you could also use a data provider like Redis. You could use a cache to store this data because remember, it's the command database that's the source of truth, and that can allow you to get really performant reads. If you take this to the absolute extreme, you could store that query view in memory in your application to give you incredibly performant reads. Now, of course, there's some whole other challenges that you need to deal with there. Come talk to me about them afterwards if you want to do that. But let's start to wrap this up a little bit now. If you're listening to this talk and you're sat there thinking, this sounds amazing, James, but I'm so far away from potentially building event-driven architecture, where exactly do I start? And my recommendation there would just be to start small. Don't try and rewrite your entire system immediately to use event-driven architecture. Pick a small part of it and then start to build that out in a more event-driven way. And you can even, if you're building a monolith, if you're building something more monolithic today, you can still start to use messaging inside a monolithic application. If you're building a modular monolith, you could have the communication between your modules, use messages, and then when you start to break this apart, you have that messaging communication, event-based communication already happening. Because remember, introducing events into your system is really powerful because event-driven architecture is fundamentally a communication pattern, a way of modeling integration between systems. And that's both the technical integration, the technical communication between services, but also the human communication about your services. One of the hardest things in software development is communication. The language that you use to talk about a system between technical and business people. And remember, it's language and words that sets us apart as humans. And whilst, at least for the moment, software development is still a human endeavor, using the right words and languages to talk about and build your system is incredibly, incredibly powerful. If you want to have any questions or you want to continue this conversation, I will hang around here for a little bit afterwards. I'll also be down on the AWS booth, down in the main conference hall. Please reach out on social media if you want to chat. I'd love to hear your feedback. This is actually my first time doing this specific talk, so I'd love to hear your feedback on that. I do have a YouTube channel where I publish a lot of content there. And the final thing I'll say is that NDC is a fantastic conference and there's lots and lots of amazing speakers here. So I am genuinely grateful that you've all come to listen to me talk this morning. Thank you all for listening.